بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف المرسلين. Heureux d'être présent aujourd'hui pour participer à ce débat scientifique pour la promotion d'une investigation doctorale présentée par Khulfa et الدين sous la direction du professeur Lazare Youssef. Il est de l'université de Guelma, département d'architecture, il est responsable du domaine. Co-dirigé par Tourné Riyad, il est de l'université, professeur de l'université de Skikda, 20 août 1955, et aussi devant un jury d'examen composé du professeur Madani Saïd, un doyen des professeurs de l'université de Sétif. Il est aussi doyen des architectes de l'Algérie, qui soit bienvenus parmi nous, avec la présence aussi du docteur Sheratia Mohamed de l'université de Guelma, département d'architecture, sous ma présidence, professeur Aqama Jamal, aussi de l'université de Guelma, département d'architecture. Monsieur Ahmed, votre travail est intitulé Hybrid Energy Renovation of Existing Buildings, Case Study of a Collective Housing in Skikda. Vous avez devant vous de 30 à 35 minutes pour présenter l'essentiel de votre travail. Ce travail sera suivi par une plaidoirie de la part de vos directeurs de thèse et co-directeurs de thèse et avec une lecture d'examination de la part des membres du jury. À vous la parole.
السلام عليكم. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين. First of all, I would like to send my big acknowledgements to the members of the jury that are present today in order to evaluate, enhance and enrich my third cycle research work within my thesis entitled Hybrid Energy Renovation of Existing Buildings, a case study of collective housing in Skikda. The work plan starts with the research introduction, followed by the definition of problematic area, then research questions, then the objectives and the hypotheses are outlined. Afterwards, the thesis structure and chapters content are presented, followed by giving an overview about the study context. Then the method workflow will be explained along with diverse materials and approaches that were used. Next, the results obtained will be presented, followed by discussion about them. Finally, the presentation will end with a summary about the study limitations together with the potential areas for future research. Introduction. Many global observations such as 1973 and 1979, oil crisis, climate disruption and rising temperatures, in addition to chronic respiratory diseases, all of these are due to greenhouse gas emissions that are generated from massive urbanization and industrialization. Also, the realization that the fossil fuel era is ending has caused significant disruptions in the global oil market. As a result, there is a pursuit for new renewable energy models and international agreements like Kyoto Protocol, COP meetings, and the Rio de Janeiro Earth Summit, which introduced Agenda 21 for development, sustainable development goals. Since independence, Algeria has seen a substantial population growth and construction boom. However, the focus on rapid mass construction has neglected considering diverse climates and passive solutions to enhance habitat performance, resulting in an uncomfortable built environment. To mitigate excessive energy resource exploitation, it's deemed necessary to diversify the national economy and invest in alternative energies. Algeria's vast renewable energy potential can help address its environmental and national challenges through an ecological, approach based on renovation of buildings in residential areas. Based on the identified gaps in the fields of solar radiation in urban areas, building renovation, integration of solar panels, energy consumption, and carbon emissions, as well as on the basis of previous investigations. The previous investigations have revealed that Skikda's collective housing is deteriorated due to historical and meteorological factors, and the lack of housing has resulted in rapid urbanization without applying bioclimatic principles, which led to comfort shortage and fails to meet energy saving actual standards. After that, the scientific position has been determined. Specific research questions can be formulated as follows. Problematic. First question, how do multi-scale factors related to the 4 collective housing building in Skikda selected as case studies impact their exposure to solar radiation, energy consumption, and carbon emissions? How does the orientation and height of an apartment affect its energy consumption when compared to the whole building in the 4 case studies in the city of Skikda? How do the different passive, active, and hybrid renovation interventions affect energy consumption, ecological footprint, as well as the classification of existing archetypes in Skikda in terms of performance in both aspects compared to European references? Considering the specific morphologies of the studied archetypes and their surroundings, the changing of the location of and the quantity of hybrid PVT solar panels integrated on the external surfaces of the buildings, what are the best scenarios associated with each case study in terms of energy demand and carbon emissions? Objectives. Evaluate the impact of spatial factors on solar energy availability and the insolation on buildings and sites in 4 study cases, identifying optimal locations for solar panel incorporation based on this evaluation. Assess the initial states of selected archetypes and their apartments in terms of energy and ecology, and identifies various multi-scale factors influencing their performance. Assess the energy and ecological performance of selected archetypes post-energy renovation to determine the best scenario for each case study, focusing on individual and synergetic effects on building performance. Analyze the effects of altering hybrid PVT solar panel quantity and positioning on energy efficiency and suitability for 4 collective housing structures, considering spatial morphological factors. Hypothesis. The thermal properties, shape of buildings, urban and topographical context directly influence solar access, energy consumption and production, alongside carbonic emissions. The apartments located on intermediate and upper floors, and also the ones that face south, are less energy consumers. Various passive and active measures can considerably improve the energy and environmental performance of residential buildings to varying degrees depending on the shape of the building space and the intervention measure. The integration of PVT hybrid panels, in particular into the roofs of collective housing, makes it possible to achieve much higher levels of energy production and environmental performance than their integration into other external surfaces of the building. This is structure. Chapter 1, entitled The Relationship between multi-scale spatial factors and energy consumption. It deals with energy requirements in urban areas, particularly for households. It describes the various multi-scale factors that affect energy consumption and solar exposure. Chapter 2, entitled Worldwide Climate Change Issue. It offers an overview of climate change, relevant international institutions, labels and conferences, highlighting the link between climate change and cities. Chapter 3, entitled Algeria's Energy Situation, Regulations and Legislation. It explores Algeria's renewable and fossil energy potential, government and private sector efforts for energy transition and legislation to improve energy and environmental national state, including thermal, energetical and ecological improvements in residential areas. Chapter 4, entitled Energy Efficiency Renovation of Buildings. It explains energy renovation is objective and methods focusing on both built and the human environments. It reviews previous renovation experiences, approaches and simulation tools used in this field. Chapter 5, it explores SCIGDA, focusing on its historical, climatic and epistemological aspects, analyzing classifications and selecting 4 archetypes at different sites. Chapter 5, it presents the method workflow and the different materials and approaches that were used. Chapter 7, it presents the results and the discussion. Study context. The North African and Algerian city of Skikda belongs to the temperate Mediterranean climate zone, which is generally humid, with summers that can be hot, but winters that are generally mild. Moreover, the city has had fascinating historical growth in the construction industry, particularly in the residential sector. According to the typological analysis, the city has a range of housing categories based on many factors over the generations. This variety in weather over the year, natural context and built environment leaves the city a unique and appealing location for multidisciplinary research. The residential samples were selected after typomorphological analysis of all existing typologies of collective habitats in Skikda according to the building's height, the age of the building, the complexity of the building's envelope, the height of nearby buildings, the distance between buildings, the topography of the site and the surrounding area. Method workflow. After reviewing documents and the previous research, as well as analyzing existing collective housing typologies, 4 study cases in Skikda were then selected. Topographical studies and visualization were done to show the elevation of study cases locations compared to the surrounding topography using Google Earth in addition to other mapping websites. The data were then organized and presented in tables and curves using Microsoft Excel. Geometric modeling was done through ArcGIS, creating shapefiles, integrated into the City Energy Analyst simulation tool. This tool utilizes Skikda's climatic data from the Meteo Norm 8. The COA tool was then provided with only the data concerning physical and behavioral properties. The simulation results were calibrated and validated using measured energy consumption data obtained from local commercial agencies of Sonargaz in Skikda. The shapefiles were also imported into Revit Autodesk for solar analysis and visualizations in order to display the variance in cumulative incident solar energy throughout 2021 recorded hourly for each urban model by the use of Autodesk Insight 360 plugin. After conducting topographical, energetical and environmental, in addition to solar analysis, the initial state of the studied archetypes was evaluated. Then the scenarios were selected for implementation based on this evaluation. These scenarios involved launching a passive intervention starting with replacing single glazing that exists with double glazing and then triple glazing windows. It involves also replacement of existing hot water energy supply system by an electrical one. Also, an introduction of photovoltaic thermal solar panels, PVT hybrid, was done in various scenarios, adjusting their sizes and locations on the vertical facades and on the roof. Many energy and environmental results were obtained and then discussed, compared and evaluated in terms of energy and ecology on the basis of simulations generated by city energy analysts. Also, the real historical energy data was in the form of quarterly bills. It was collected for some ground floor, commercial and administrative premises, in addition to 21 apartments which are situated in the 4 buildings studied through sampling based on their height and orientation in relation to the whole building. Approaches, multi-scale approach. In this study, many approaches were utilized, notably multi-scale approach. Multi-scale reasoning is based on the consideration of several levels of scale, given that now scale is independent of the others, which justifies the choice of this approach. Urban building energy modeling reduced order bottom-up approach. COA, which was used in this research as a principal tool, follows the reduced order IBM approach, which is widely used to do quick analysis of building and urban scale performance. This approach needs fewer inputs than the physical and data-based approach. One of the processes specific to this approach is the determination of model parameter values, which can be estimated using various calculation standards developed by International Organization of Standardization and the European Committee for Standardization. 3D model-based approach. The urban environment may be modeled via 3-dimensional characteristics with exposure to sunlight simulations. The solar irradiation may be calculated while taking into account building obstructions via comprehensive models or using adjustment factors that reduce the entire roof or facade area in order to get the appropriate area for solar energy systems. Bayesian inference approach. This approach was used for calibration, where prior distributions are updated and adjusted depending on experimental or measured data, to finally obtain a posterior probability distribution, including the information contained in the observation, on the basis of Bayes' theorem, using Monte Carlo simulation, a method which is based on prediction, probability, and repetition, starting with the prior random variable. Results and discussion. Before renovation stage, topographical analysis at mesoscale level. On the basis of topographical analysis, study cases A, C, and D are more protected from the prevailing cold winter winds than study case B, which is more exposed to these winds, which come from limited directions between north and west, where the strongest are determined to be from west-northwest, according to the wind draws of the city of Skiga. Solar analysis at neighborhood and local shading scale. According to the 3D solar mapping, the ideal locations for solar panels are high-altitude empty sites far from shading effect, while unobstructed roofs come second. South-facing upper facades are the third best locations for solar panels, as they benefit from a large amount of annual solar energy. East and west facades are also good options when it's installing panels on roofs, or south-facing facades is difficult or impossible. However, north-facing facades are not recommended for solar systems. Effective integration of solar panels is achieved through simple architectural designs without excessive extensions or setbacks. During the hottest months, from May to August, in the 4 case studies, the roof receives the highest radiation percentage. The south face, the surfaces of cases A, C, and D, as well as the west-facing facades of case B, receive the greatest percentage for the rest of the year. This is because the sun's height angle is higher in summer and lower in winter. Therefore, it's suggested to use the roof and south-facing surfaces for integrating hybrid PVT panels during renovation scenarios. Energy analysis of measured data at architectural scale. According to analysis of measured real data for the 4 cases under study, gas use was much higher than electricity use, and both gas and electric consumption were generally higher in the oldest archetypes, which were constructed with less insulation capacity. The exception to this was during the coldest months, when the highest gas consumption was recorded in archetype B, which is the most recent building, but is also the most exposed to the prevailing winds. The linear regression between annual and solar radiation and energy consumption per unit area showed a weak negative correlation between solar radiation and energy consumption, suggesting that the impacts of building and surrounding environment's morphology was weak and didn't significantly affect energy consumption compared to the other factors. Bayesian calibration and validation. The predicted and measured total energy use were compared, and the calibration findings after numerous attempts showed acceptable annual error percentages and acceptable CVRMSE and NMB coefficients values. As a result, the energy models have been validated annually and monthly in accordance with ASHRA Guideline 40/2002. Energy analysis of simulated data at architectural scale. On the basis of simulated monthly energy consumption bar charts after calibration and validation, heating and hot water accounted for the highest energy demand in the 4 case studies. These needs were mostly met using natural gas, detrimental to the environment and the human health. The electricity use is for lighting and domestic equipment was minimal and marginal. The polynomial regression revealed that an overuse of heating was detected, in contrast to the air conditioning, which was rarely used. This conclusion is based to the hours of use of both the systems in the recommended temperature range. This could be due to physical, behavioral, or financial factors, knowing that electricity is more costly than gas. Environmental evaluation of simulated data at the architectural scale. The environmental simulation indicates that operational carbon emissions in 2021 are very higher than intrinsic emissions in all 4 case studies. Total intrinsic emissions rise with a larger gross floor area, while intrinsic emissions per floor area decrease with the increase in gross floor area. With no overperformance or carbon over emission, the 4 archetypes are categorized as medium greenhouse gas emitters based on analysis and environmental assessments conducted by using European benchmarks, notably Italian, Spanish, and French. Comparing at the energy analysis and evaluation of measured data at apartment scale. Comparing apartment floor heights and orientations confirmed the negative correlation between solar radiation accessibility and energy consumption, where lower floor apartments and north-facing apartments consumed more energy. The evaluation of the energy consumption of the 21 apartments that fit into the 4 cases showed that most of them are classed as medium consumers, while the remaining dwellings are classified as higher energy consumers. Post-renovation stage. After baseline situation was evaluated, a number of energy renovation scenarios were introduced, where some of them are based on one type of interventions, while others study the synergy between many types of interventions. The analysis of the percentage of the reduction or increase in annual energy consumption for gas or electricity or overall energy consumption, in addition to annual operational greenhouse gas emissions for each study cases, showed many outcomes. Some of them are gas consumption decreased the most in study case B after adding more high performance windows due to the building's high vulnerability to winter lines. However, the additional glazing panels reduced the natural light level and led to an increase in electricity use for artificial lighting. Scenario PR6 also sees an increase in electricity consumption due to the replacement of initial natural gas-based supply system with the electric boilers. The study, which compared hybrid PVT panels on south-facing walls and roofs, showed that roof panels yielded significantly higher thermal production for the same surface area, while electricity production increased slightly on roofs comparing to the south-facing walls panels. The solar panel surfaces added to the south facade led to more production of electrical energy than thermal energy, which was slight. All above showed that the number of solar panels affects electricity production, while the cumulative insulation per unit area over the time affects thermal energy production. Knowing that roofs having higher insulation rates than the facades. The effectiveness of heat loss reduction from insulation during building renovations depends on the exposure to weather fluctuations, while the energy production from PVT hybrid panels relies on the building envelope morphology. The study analyzed various variables and found that behavioral, urban, topographical, and solar characteristics interrelate and affect environmental conditions and energy use. Each archetype is characterized by its envelope and urban and topographical environment, causing them to react differently to the same situations, with some ideal settings being less suitable for the others. These tables present energetic and ecological assessments of each of the 4 study cases before and after each scenario. They showed that combination using triple glazing paired with hybrid PVT solar panels on the roofs provides a sufficient scenario with lower requirements and high energy and environmental performance based on European benchmarks. For cases A and C, 6 meters square of roof space per apartment was needed, while for case study B, 12 meters square per apartment was required. However, for case study D, the most eco-friendly option was to install 12 meters square of panels per apartment on the south-facing facades and use electric boilers for hot water supply. The most energy efficient solution for archetype D is to divide the surface and area equally between the roof and the south-facing facade. The synergy between the different measures their degree of use, their careful selection and strategic positioning have led to better energy and ecological outcomes. During scenarios when several interventions were used in one scenario, energy and ecological performance levels increased to the point where in certain cases energy consumption are highly reduced and ecological footprints are almost nil. It's recommended to adopt the seasonal thermal energy systems due to the negative correlation between monthly thermal panel production and heating high demand period. Conclusion. In the light of climate change, this study, which focused on Skikda's collective building stock, could offer Algerian energy decision makers a vision for the future in terms of controlling energy consumption in one of the most energy intensive industries and reducing ecological footprint. Clean energy transition can also be facilitated by promoting the renovation of the urban stock by means of the synergy that could be through use of efficient appliances and boilers in the building sector, reinforcing the envelope, integrating renewable energy systems, and raising awareness among households, particularly in areas with significant solar potential. Study limitations. The collection of energy data for solar gas commercial agencies was challenging due to the consistent occupation of workers and the difficulty in retrieving archives. The data was collected through sampling, which may introduce uncertainty due to varying energy consumption among dwellings and individuals. The COA tool used simplified archetypes as part of a reduced order approach, but this may limit its ability to handle complex facades and roofs. The Meteornorm tool generates simulated climate data which does not reflect ideally real-time weather fluctuations. The lack of an Algerian energy and environmental benchmark in this study led to the use of European benchmarks from countries with similar climate to extreme northern Algeria according to Copenhagen climate classification. European benchmarks varied energy and environmental classifications for the same apartments or buildings, highlighting the need for Algerian specific benchmark and labels considering various national aspects. Future perspectives. Future research should consider economic and social factors, including cost-benefit studies and sociological evaluations of the attitudes of occupants towards innovative interventions and renewable energy technologies. The study's simulation tool don't consider the effects of tree on shading and the microclimate. So combining these tools with vegetation specific tools may yield more accurate results, especially in the cases that no presence of significant tree coverage. This study was conducted in one city and one climatic context. Future research using multi-scale reflection and considering case studies in different climatic contexts may uncover new insights. Energy analysis can be done on a large scale, even for whole cities, making research on the basis of tools like COA interesting for sustainable city planning and renovations, expanding the scope of energy analysis to the entire city. More details about my doctoral participations in conferences, 7 international conferences, 3 national conferences, articles, 1 national article, 3 international articles, internships, short-term internship in the University of Karabakh in Turkey. Details about the thesis. Number of pages 367. Language English. Percentage of plagiarism 9%. Thank you for your attention.